Thank you. Imagine you're sitting here. Put yourself in the seat of the pilot and overlook the fact that it's actually standing on the ground in this picture. Imagine that you're in the air and you're the pilot of this really, really complex machine. Quite a scary challenge and task. And then, with your critical systems you are depending on in that seat, you get this. We all know this blue screen of death, of course. The thing is, in the context we are in now, we are completely dependent on critical information from our digital systems. And this happens. It could be a bug. It could be an attack, a worm just waiting idly in the system and then suddenly kicks in. What do we do? I think this is a really interesting thought experiment with putting ourselves in a position where we are really, really focusing on safety. Safety is the ultimate goal. Of course, it needs to be secure as well, but safety is the ultimate goal when we're sitting in the plane. We want to survive, and we go into survival mode. On ourselves, for ourselves, and also for all the passengers. So how do we cope with this situation? So in the air industry, there's 3 golden rules. That's really important to always sort of have in the back of your mind, kind of the reflex when things happen. I heard about this a while ago, and I felt that it's really sort of connected to what we should be thinking in OT cybersecurity as well. The number 1 rule is to aviate. What does that mean? It means to continue flying. Continue, just don't shut down and sort of run away. You need to actually handle the situation. You need to continue flying, or else you die. So you need to continue handling the situation. Something needs to be done. You need to fly. Also connects to the focus we now get on resilience. It's really important to continue our critical business. So we need to continue flying. What else do we need to do? We need to navigate. We need to understand where we are now and where we need to be in order to save all the passengers. We have to navigate, and we are dependent on a lot of information to be able to navigate. And when we are dependent on information, what do we need to do to sort of validate the information, get more information? We need to communicate. So we need to have more input from the people around us and the systems around us, and we also need to provide information to others through communication. We can't shut down these sort of core functions when we are in a critical situation. So with bringing these sort of principles into general OT cybersecurity, I think this really helps us in putting the priorities straight. Continue flying, we need to navigate the environment and the sort of the risks around us, and we need to communicate. We can't just shut down. Within IT, how have we handled the problems with out-of-band problems, where the software stops behaving as it should? Windows isn't able to handle the situation. It goes into a blue screen. What happens afterwards is that you get an option of going into safe mode. That's a kind of cool way of handling it. You go into a degraded mode. Not much actually works, but you get into Windows and you can start to troubleshoot. So that's a cool principle to bring with us, the degraded mode. I would like to see more of safer modes, more granular, not a binary world where we would just shut down 1 or 0, but we actually go into several different safer modes. And we already have that in industries, but I would like to see more of it. more granular safer modes to be able to handle the changing risk levels we have around us. So in my car, for instance, I get this error message from time to time. And the thing I would like to highlight is full performance not available. It goes into a degraded mode, and it down prioritizes performance to be able to handle the risk. I really like that principle. So when we look at safety instrumented system, the brain in the machinery and in the factory and in the systems, the brain that has the only purpose of handling safety critical situation, bringing the machinery to a safe state. This is an excerpt from 62443, showing where the safety instrumented system usually sits within a large control system. And it's sort of put on the side of the control system or the process control system. And its only purpose is to take action when things get scary. It's really a simple world for the sys. It's a binary world, zeros and ones, and it's, I hear people say it's kind of the stupidest system in a control system. Really simple stuff. The thing that the safety instrumented system is doing is taking input from sensors, doing some voting algorithms, and then choosing what actions to perform. And it's about 1 out of 2, 2 out of 2 kind of voting rules. And when doing engineering of safety instrumented systems, you can choose in the voting rules between focusing on safety, high safety. Only one sensor is enough to go into fail-safe. Or you can do focus on high availability. Then you need multiple sensors to fire before you actually go into fail-safe. So that's interesting to keep in mind when we do engineering. And also when we move into incident response and need to handle a situation like in the plane. Should we focus on high safety or high availability? Often the solution is actually a combination of them. But this is the simple world. The easy world, actually. Because what about high security? Then things to get really messy and difficult. The safety world, like I said, is kind of simple. Binary, 0 and 1. We have perhaps the nature as our threat. But in security, we have people and humans, creative humans, as our threat. And also creative programmers, leaving behind lots of strange bugs. So then when we try to combine security into this picture, things get challenging. So what do we do then as a community? I was challenged by Dale to bring forward some pillars of the operational safety instrumented systems. How are we able to build safety instrumented systems that also are able to handle or take cybersecurity information as inputs? When I were working on this presentation, I had a thought of actually getting 5 pillars. That's also always good to present 3 or 5 pillars. But I see that there are crazy amount of challenges going forward to have a really proper safety instrument system that is able to take cybersecurity inputs. Because the cybersecurity landscape is messy. Lots of uncertain data. Lots of missing knowledge in our assessments. And based on that kind of data, crappy data, basically, we need to take decisions that are safety critical. So I've chosen 5 challenges that we need to overcome. We can call them pillars or tenets, but I see them more as challenges that we as a community need to overcome going forward, creating products, using real engineering processes, so that we actually can get an operational safety instrumented system that is able to save our lives when cybersecurity threats are sort of changing and arising. So what is one core principle of this safety instrument system? Of course, it's all about safety. Well, almost. Because safety information is not enough now when we are being challenged by cybersecurity attacks. Cybersecurity information needs to be taken into the picture, into the voting somehow. All of the systems and all of the components in our control system need to be inherently safe. They need to be safe by themselves, or secure by themselves, secure by default, secure by design. I would like to actually propose that we quit talking about secure by design and talk about safe by design, or at least safe and secure by design. Because the end goal, in my opinion, isn't security, it's safety. And for actually having a proper focus on safety, it needs to be consequence-focused. Probability, we keep discussing with clients all the time about probability, and it's really difficult making the sort of the picture of information much more complex. But if we can focus on consequence, potential impact, worst case scenario, that brings the discussion into a much more fruitful level, in my opinion and experience. I've been looking through some research papers on sort of how we are able to bridge the gap between cybersecurity and safety, especially functional safety. So they talk about cyber-informed safety or safety-informed cybersecurity. That's two different ways of actually looking at the challenges with two different end goals. So this research paper is a meta-study of all the different research papers that have been done on the combination between cybersecurity and safety. I find it really interesting. Tells us a bit about our challenges going forward, but also quite much about where we are today. So it looks, for instance, on the goal that these papers sort of, or methods focus on. Is it combined safety and security, harmonizing them? Is it about safety-informed security? Or is it about security-informed safety? Where are sort of the temperature in research and academia nowadays? Are we focusing on security or safety, or trying to actually combine them? In the study, they find that they analyzed 68 different methods from all across the world. And 30 of them, the major part of them, are security-informed safety. I think that's really good. Safety is the end goal. And cybersecurity needs to provide input to safety decisions. And that also brings me to what we see lots of over here in the States. I really find interesting work. You have the CCE, Cyber-Informed Consequence-Driven Engineering, or Consequence-Driven Cyber-Informed Engineering. Taps into the same perspectives of consequence focus and safety as the end goal. If it's possible to actually engineer away cyber risk, why don't we do it? Instead of just mitigating it or reducing the risks, we can actually use proper engineering techniques to remove them. And of course, the cyber-informed engineering, that's been worked on quite much now. I find this research or this kind of maturing work really interesting, and we need to focus more on it. And also engineering-grade security. When we can do it really bulletproof, non-hackable, why don't we do more of it? Completely removing the cybersecurity risks for critical, especially critical areas. Another aspect or pillar or challenge that we need to overcome then is inputs. Inputs into the safety decision that needs to be taken. When you're in the plane, flying the plane, and the blue screen comes, or you're actually experience lots of instability and irregularities in the systems, you're dependent on a lot of input, good quality data. The problem with the whole cybersecurity area, that it's messy data. We can't trust the threat intel. We can't trust the level of visibility we have. Perhaps it's only 5% visibility we have. We can't trust that we found all the vulnerabilities. There are always more and more vulnerabilities, so we can take for granted that there's always 0 days. Yeah, even though the adversaries don't need to use them, but that they will always be in the system, the 0 days. So it's lots of messy input that we need to bring into the picture to be able to provide the necessary information over to the safety system that will sort of take the bigger decisions. So cybersecurity becomes a provider of good quality data. And that's a really big challenge for us as a community. We see also from an architectural perspective that we are moving into a world or architectures that are sort of making the picture more complex. The Purdue model is dying. We move into a sort of a messy architecture. Everybody talks to everybody. How can we trust data when everybody just talks to everybody? It's kind of noisy, spaghetti. And we work on digital twins, or what is called in IEC, the asset administration shell. Here we can more easily see that everybody talks to everybody. Everybody is supposed to provide information and consume information. What I think is interesting with this picture is that every component and every part of the system need to focus on its own security. We can't rely on a top system or a DMC or a perimeter system to sort of be secure and safe. In the future, going forward, every component needs to be safe and secure by design and by default. Not only secure by design, but safe and secure. Jumping back to the study, to be able to grasp a bit about where we are, how much progress have we been doing in the gap or in bridging safety and security, the study looks at whether the methods are quantitative or qualitative. In research views, when you're only doing qualitative studies, then you have not progressed much in actually trying to model the reality. So what we see here in this meta-study is that 41 of the methods are qualitative. Really early work in the science area where we are not able yet to model reality in a proper way. So we are trying several different ways of doing it. And we really need to invest a lot of good people in this work to be able to model it properly and get models that actually can predict risk levels, for instance. Another area we need to solve or jump into is how we can, over time, make the safety instrumented system better and better, or keeping ashore with the changing threat landscape, changing vulnerability picture. New systems brought aboard. We changed the remote access system. All these kind of things change the neighboring environment, and the safety instrumented system need to be able or needs to be informed about these things so that it can take the right safety decisions according to the sort of running risk picture. So it needs to be, we need to have continual supervision of the system. We can't just set and forget it. We need to help it, monitor it, train it, ensure that it works all the time, test it. So we need to test it continuously and rigorously. We need to validate it, perhaps through third-party validations, or at least third-party validation, bringing on board the best people we know of and can get a hold of to do proper validation of it. And supervised learning. The system actually needs to learn. Things change, technology change, threat change. That's a supervised learning. We move into AI, machine learning, those kind of things. And when we combine that with safety instrumented systems, that's sort of things you shouldn't mention in the same sentence, but we actually need to do it to be able to handle the risks we see nowadays, and we will see going forward in the future. And it's all about giving the safety instrumented systems, the safety engineers, a model of the real world around us. So it needs to be able to sort of do continuously modeling, assessing, and prediction of the risk. We, of course, nowadays need to have a lot of people involved in this to be able to predict risk, to handle uncertainty in all the data, complex data. But more and more we need machinery to do these decisions for us. They need to be able to handle information about integrity, safety, of course, and security, or cybersecurity. Quite a big scope for a digital system to handle information about. In SINTEF in Norway, we have been working, I'm not from SINTEF, but I'm joining this, this work from time to time on the C-RAMP model, continuous risk analysis and mitigation process. This is a model and a process which is trying to bridge the gap between cybersecurity and functional safety. Actually, it doesn't have an acronym, but when I was preparing for this conference, I felt that, of course, every good model needs to have a good acronym. So I talked with the SINTEF people, and we thought that C-RAMP could work. I didn't feel CRAMP was that good, so it's C-RAMP. But it's a continuous process. That's what I'm trying to show in this picture, a continuous process of information sources, inputs, assessment, threat assessment, risk analysis, relevant actions, and then going on with this continuously. And that gives us the possibility to use this continuous process in the whole life cycle of a plant or a facility, but also in operation for split microsecond decision, for instance, in the safety instrumented system. The model also goes into much more details about what this actual cycle is about. Where is the sort of the main inputs? What kind of data do we need? Very interesting stuff. How do we do decisions and voting, validation of the data? What kind of outputs do this kind of system need to produce? And what kind of feedback do you need to have? Interesting model. But we need to do more work on this. We need to research it, bringing together the whole community and also other disciplines, functional safety, mechanical engineering, people with really deep level understanding of the threat picture, those kind of people. Everybody needs to be involved to see if this model or process actually will be a good model of bridging the gap between cyber security and safety. Okay, if we go over to the output side, the safety instrumented system needs to take some actions. It's often called effects, but we can also call it actions. What I see is that the actions needs to be more variable and granular. It's not a binary world where we just shut down. We need to build in resilience into the system. Like I showed you from the picture from my car with degraded performance. When risk levels increase, we need perhaps to actually drive slower. And that could be an automatic process. When the facility actually, or the safety instrumented system, the brain of the facility, understands that the risk levels in the neighborhood, in IT, in the cloud, down in the sort of mechanical barriers, they stopped working. Last maintenance or testing showed that the non-hackable barrier actually doesn't work anymore. Then you need to sort of do some actions where you vary your output, you vary your performance, you reduce your performance, you actually drive slower. So what I'm dreaming of is that we focus on research and experimentation and testing on this area, and we get into an area where we can actually do predictions for the future risk, the short-term future risk. So by using trends on the risk level, this safety instrumented system is looking at, This is sort of how it predicts the future risk. So then we are in normal mode operations. We drive at full speed, full production, full performance. But later on, when you start to predict that the risk levels are increasing above a bit more unacceptable level, then we go into safer mode, level 1, for instance. We drive slower. And if the predictions, short-term predictions, actually show us that we are above completely unacceptable levels, of course, it's a prediction, so it's not for sure that this will actually happen, but the risks are definitely there to be unacceptable high. What do? We have to move even more into safety, a safe state. So we perhaps go actually shut down if we are possible to shut down. We couldn't do that on the plane, but in other facilities, we can actually shut down, evacuate. But it's a higher level of safety we go into, more degraded performance. So with this, I hope that I've been able to provide some inspiration to areas we need to explore as a community. I hope that we are able to produce or deploy systems that are properly able to handle the cybersecurity area, cybersecurity threats, and the functional safety area, with the end goal of keeping people safe and society safe. So we need to share ideas and perspectives to be able to do this. And in the end, we perhaps, I'm not sure if we are actually able to do it due to the different complexities involved, but we perhaps are able to harmonize availability, safety, and security. Okay, thank you.